What if I told you the universe is hiding its most astonishing secrets just out of reach, not in the familiar glow of stars or the swirl of galaxies we can see, but at the very edge of everything we know? Picture standing on the shore of an endless cosmic ocean, staring into the darkness where the known dissolves into mystery. Out there, beyond the farthest flickers of light, lie phenomena so strange they defy our understanding. Black holes that shouldn't exist, forces that rewrite the laws of physics, and whispers of dimensions beyond our own. This isn't science fiction. It's the frontier of human discovery, and today we're setting sail into the unknown to uncover 30 of the most baffling enigmas lurking at the edge of the universe. Think about that word edge for a moment. We use it like it's a boundary, a finish line, but in a universe that's expanding faster than light can chase it, where space itself stretches like taffy, the edge isn't some distant wall. It's a shifting, shimmering horizon of questions. What happens when you reach it? Is there something or nothing? And how do we even begin to study a place so far away that its light hasn't reached us yet? The answers might rewrite everything we think we know about reality. From rogue planets drifting in eternal exile to cosmic voids so empty they shouldn't exist, the outskirts of our universe are a playground for the bizarre. This journey isn't just about cataloging weird phenomena, it's about peering into the abyss and realizing how much we don't know. Every mystery we uncover forces us to rethink our place in the cosmos. Are we alone? Are we special? Or are we just tiny specks clinging to a speck of space in an infinity of unanswered riddles? Stick with me, because by the end of this you'll see the universe, and maybe even yourself, in a way you never have before. Ready to dive into the unknown? Let's go. Somewhere in the depths of space, hidden behind the thick curtain of our own Milky Way, something immense is pulling entire galaxies toward it with irresistible force. Scientists call it the Great Attractor, and it's one of the most baffling gravitational mysteries in the cosmos. Imagine floating in a river where the current tugs you toward a waterfall you can't see. That's what's happening to thousands of galaxies, including our own, as they drift toward this invisible cosmic magnet. But here's the catch: we can't even see it clearly. The Great Attractor lies in what astronomers call the zone of avoidance, a region of the sky obscured by the dust and stars of our galaxy's disk. It's like trying to peer through a dense fog, catching only glimpses of the colossal structures beyond. What little we can observe suggests this gravitational beast isn't acting alone. Behind it, an even larger structure known as the Shapley supercluster may be pulling the strings, creating a cosmic tug-of-war that stretches across hundreds of millions of light years. So what is the Great Attractor? Some theories suggest it's a supercluster of galaxies so massive its gravity warps spacetime itself. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, could be twisting the fabric of reality in ways we don't yet understand. One thing's certain: this isn't just a curiosity. The Great Attractor could hold clues to the fate of our galactic neighborhood, dragging us toward an unknown destiny at over 600 kilometers per second. Think about that for a moment. Right now, you're not just sitting still. You're hurtling through space, caught in a current set in motion billions of years ago, toward something we can't fully see or comprehend. The scariest part: we might never reach it. The universe's expansion could stretch space faster than we're moving, leaving the Great Attractor forever just out of reach, a cosmic siren calling us into the dark. Now picture a hole in the universe so vast you could fit 60 Milky Ways lined up end to end inside it, and still have room to spare. This is the Boötes Void, a spherical region of space spanning 330 million light-years where almost nothing exists. No galaxies, no stars, just an unsettling emptiness that defies everything we know about how the cosmos organizes itself. Astronomers call it a supervoid, but that doesn't quite capture just how wrong this place feels. The universe is supposed to be clumpy galaxies huddled in clusters, strung along filaments of dark matter like beads on a cosmic web. Yet here, in the heart of Boötes, there's almost nothing. Of the few galaxies that do linger in this void, many seem strangely isolated, as if they were marooned there by some unseen force. It's like walking into a city where every neighborhood has been abandoned, with only a handful of flickering porch lights hinting at life. So how did this cosmic desert form? One theory points to quantum fluctuations in the early universe, tiny ripples in space-time that, when stretched by inflation, left behind pockets of eerie emptiness. Another, more unsettling idea suggests advanced civilizations might have engineered this void, harvesting all available matter until nothing remained. Imagine a civilization so advanced it could dismantle galaxies like Lego sets, leaving behind only clues in the darkness. But the most plausible explanation is also the most humbling. The Boötes Void might just be a statistical fluke, a random bubble in the foam of the cosmos. Even in an infinite universe, probability dictates that somewhere there will be a place where almost nothing gathers. Yet that doesn't make it any less unnerving. Because if such a void can exist, what else lurks in the gaps we haven't found yet? Stare into this emptiness long enough, and you start to wonder, is the universe supposed to make sense, or are we just grasping at patterns in the dark? And here's the twist: the Boötes Void isn't just sitting still. It's expanding, its edges stretching as the universe accelerates outward. One day, far in the future, even those few stranded galaxies might vanish, leaving behind perfect, infinite nothingness. A reminder that in the grand theater of the cosmos, emptiness might be the most powerful actor of all. Even as the Great Attractor tugs at our galactic neighborhood, there's something far stranger happening on an even grander scale. A phenomenon so puzzling scientists named it dark flow. Picture this: hundreds of galaxy clusters, each containing thousands of galaxies, all streaming through space in the same direction, like leaves caught in a cosmic wind. But here's the twist: there's no visible source pulling them. No supercluster, no black hole, nothing we can detect. It's as if the universe itself is tilting towards something outside our observable horizon, a gravitational shadow we can't see. This isn't just a slight drift. These clusters are racing at speeds exceeding 2 million miles per hour, all toward a single point in the sky near the constellations Centaurus and Vela. The sheer scale of this motion defies everything we know about the universe's structure. Gravity should balance out over vast distances, leaving no preferred direction for matter to flow. Yet the dark flow persists, stretching billions of light-years far beyond where any known mass could exert such influence. So what's behind it? One radical theory suggests the pull might come from another universe. Yes, you heard that right, another universe, brushing against ours in the multiverse's unseen tapestry. Imagine two soap bubbles floating in a sink, their edges barely touching. The gravity from a neighboring bubble could, in theory, tug matter from our own, creating this eerie, coordinated drift. It's a mind-bending idea, but not impossible. If true, dark flow would be our first tangible hint of a reality beyond our cosmic bubble. There's another, equally wild possibility, that the universe isn't uniform after all. The Big Bang's afterglow, the cosmic microwave background, shows slight temperature variations, tiny wrinkles in space-time. Some scientists think these wrinkles might trace back to an uneven distribution of matter in the primordial universe, a lopsidedness so profound it's still guiding the motion of galaxies today. But here's what keeps astronomers up at night. If dark flow is real, it means there's something big out there, something so massive it bends the rules of cosmology. And we may never see it. The expansion of the universe could be carrying it away faster than light, leaving us with only the ghostly fingerprint of its gravity. A mystery pulling us toward the unknowable, reminding us just how much of the cosmos remains hidden in the dark. We might feel like cosmic royalty living in the Milky Way, but here's the humbling truth. our galactic neighborhood is floating inside one of the universe's emptiest rooms, the KBC Void. Named after the astronomers who discovered it, Keenan, Barger, and Cowie, this colossal bubble stretches over 2 billion light-years across, making it the largest known void in existence. And we're right in the middle of it. Picture a balloon with a handful of glitter inside, most of it clumped on the edges, leaving the center eerily sparse. That's us, a few scattered galaxies adrift in a sea of near-nothingness. But the real mystery isn't just the void's size, it's what this emptiness means for our understanding of the universe's expansion. You've probably heard of the Hubble constant, the number scientists use to measure how fast the cosmos is stretching. Here's the problem: depending on where we look, the numbers don't match. Measurements from nearby galaxies suggest a faster expansion rate than those taken from the afterglow of the Big Bang, and the KBC Void might be the reason why. Think of it like running through a crowd. If you're in a dense mob, you'll bump into people constantly, slowing you down. But if you're sprinting across an empty field, you'll move faster with nothing holding you back. Our galaxy's location in this underdressed void means we're essentially in that empty field, less gravitational drag from surrounding matter, making nearby space seem to expand quicker than it really is. It's a cosmic optical illusion, one that could explain why our local measurements clash with those from the early universe. Now, here's where it gets even stranger. If the KBC Void is real and not just a statistical fluke, it challenges one of cosmology's bedrock principles, the idea that the universe is roughly the same everywhere when you zoom out far enough. Called the cosmological principle, this assumption guides everything from galaxy formation models to dark energy theories, but a void this massive throws a wrench into that tidy picture. How could such a lopsided bubble form? Did some titanic force carve it out, or is the universe far more uneven than we ever dared imagine? Some scientists argue the void could be a fossil from the universe's infancy, a relic of quantum fluctuations stretched to unimaginable scales by inflation. Others wonder if dark energy, the mysterious force accelerating cosmic expansion, behaves differently in these barren regions, sculpting voids like bubbles in boiling water. And then there's the spine-tingling possibility that we're not in a special place at all, that the cosmos is riddled with voids this size, and we just haven't found them yet. But perhaps the most unsettling implication is this: if our measurements of the universe's expansion are skewed by the void, what else are we getting wrong? The Hubble constant isn't just some abstract number. It's the yardstick we use to measure the age, size, and fate of everything. A discrepancy here could mean recalculating the universe's timeline, or even rethinking how dark energy works. It's like discovering your tape measure has been stretched all along, throwing every blueprint into doubt. So next time you look up at the night sky, remember, those glittering stars aren't just above you, they're the few neighbors peeking through the cosmic fence of an unimaginably vast emptiness. And the more we learn about this void, the more we realize how much it's quietly shaping our view of everything beyond it. What if the universe has a hidden axis, a cosmic spine running through space that shouldn't exist? This isn't the plot of a sci-fi novel. It's a real, unresolved puzzle in cosmology known as the axis of evil, and it's throwing everything we thought we knew about the universe into question. The story begins with the cosmic microwave background, the afterglow of the Big Bang, a snapshot of the infant universe frozen in time. This faint glow should be random, like static on an old TV. But when scientists mapped it, they found something unsettling: patterns. Not just any patterns, but a bizarre alignment stretching across the sky like an invisible arrow, pointing toward a direction that defies all expectations. Imagine tossing confetti into the air, only to watch it arrange itself into perfect lines instead of scattering chaotically. That's the level of weirdness we're dealing with. The so-called axis of evil, a name borrowed from a throwaway joke in a scientific paper, refers to this unexpected alignment in the CMB's temperature fluctuations. Some regions are slightly hotter, others cooler, but instead of being randomly distributed, they seem to line up along a preferred axis, as if the universe itself has a north and south pole. And that's a problem. According to the cosmological principle, the universe should look roughly the same in every direction, with no privileged spots or axes. Yet here we are, staring at a cosmic fingerprint that suggests otherwise. So what could explain this? One camp argues it's just a fluke, a statistical illusion that'll vanish with better data. After all, the universe is vast, and even random noise can sometimes look ordered if you squint hard enough, but others aren't so sure. The alignment persists across multiple datasets, and the odds of it happening by chance are astronomically low. Could it be evidence of something deeper? Some theorists propose the axis hints at a pre-Big Bang structure, a shadow of whatever existed before our universe began. Picture a pane of glass shattering. The cracks might follow hidden weaknesses in the material. Similarly, the axis could be a relic of some primordial asymmetry, a scar left by forces we can't yet imagine. Then there's the multiverse angle. If our universe is one bubble among countless others in a foaming sea of realities, collisions with neighboring bubbles could have left marks on the CMB like bruises from a cosmic fender bender. The axis might be the echo of such an encounter, a tilt in space-time imprinted by a long-ago brush with another universe. It's a wild idea, but not impossible. And if true, it would mean the Big Bang wasn't a clean start. It was messy, tangled with remnants of something older, but the most unsettling possibility. That we're seeing the handiwork of an unseen force still shaping the cosmos today. Dark energy, dark matter, or something even stranger could be warping the universe on scales so vast we're only now glimpsing the edges of its influence. The axis of evil might be the first clue that our universe isn't just expanding. It's being pulled, twisted by forces beyond our current physics. Here's the twist: the axis isn't just a scientific curiosity. If it's real, it forces us to rewrite the rules. The cosmological principle underpins everything from galaxy formation to the very equations describing the Big Bang. Toss it out, and the foundations of modern cosmology start to crack. Maybe the universe isn't as uniform as we thought. Maybe it's lopsided, shaped by processes we've yet to uncover. Or maybe, just maybe, we're seeing the universe from a skewed angle, like ants trying to map a mountain while standing on its slope. Whatever the answer, the axis of evil remains one of cosmology's most tantalizing mysteries. It's a reminder that even our best theories are provisional, sketches of a reality far stranger than we dare assume. And until we solve it, that eerie alignment in the sky will keep whispering the same unnerving question: what if we've been reading the universe wrong all along? Buried in the cosmic microwave background, that ancient light from the infancy of the universe, there's a chilling anomaly scientists call the cold spot. It's not just a slightly cooler patch. This region is unusually cold, defying even the most generous margins of cosmic randomness. Picture pressing your hand against a foggy mirror and seeing one spot stay stubbornly icy while the rest warms up. That's the level of peculiarity we're dealing with here, a cosmic frostbite that shouldn't exist. At first glance, the leading theory seemed straightforward. Maybe it's a supervoid, a vast emptiness in space where fewer galaxies mean less gravity, allowing light passing through to lose energy and cool down. It's like walking into a freezer. The absence of heat makes everything feel colder. But when astronomers mapped the region, the numbers didn't add up. The cold spot's temperature drop is 10 times larger than any known void could explain. It's as if we blamed a breeze for knocking over a skyscraper. The scale is just all wrong. That's when things got interesting. Some researchers proposed an even wilder idea: cosmic texture. Imagine spacetime as a stretchy fabric, mostly smooth but occasionally knotted. If one of these knots, a defect left over from the universe's rapid expansion, unraveled, it could release energy in a way that leaves behind a cold imprint. Think of it like pulling a snagged thread from a sweater, leaving behind a tiny, distorted patch. If true, the cold spot might be a fossil from the universe's first trillionth of a second, a relic of physics operating at energies we can't even replicate in particle colliders. But the most mind-bending explanation, the cold spot could be a bruise from a collision with another universe. In the multiverse scenario, our cosmos isn't alone. It's one bubble in an endless froth of realities. If another bubble universe bumped into ours long ago, the energy from that impact might have left a mark on the CMB, like a fingerprint smudged in cosmic dust. The cold spot would be the shadow of that encounter, a ghostly handshake from a reality we'll never see. Here's what makes this mystery so thrilling. Each possible explanation leads to a completely different vision of reality. A supervoid would mean our maps of the cosmos are missing something massive. Cosmic texture would rewrite our understanding of the universe's infancy. And a multiverse collision, that would be the first tangible evidence of worlds beyond our own. The cold spot isn't just a scientific curiosity, it's a Rosetta Stone for decoding the universe's deepest secrets. And the plot thickens. Recent observations suggest the cold spot might not be entirely empty. A few faint galaxies drift within it, their light stretched and dimmed by cosmic expansion. If these galaxies are part of a larger, unseen structure, their gravity could be warping the CMB in ways we don't yet understand. It's like discovering a hidden room in a house you thought you knew suddenly. The blueprints don't make sense anymore. So where does that leave us? The cold spot refuses to fit neatly into any single theory. It taunts us with possibilities, each more extraordinary than the last. Maybe it's a flaw in our measurements, a cosmic illusion. Or maybe it's the first crack in the facade of our understanding, hinting at physics beyond Einstein, beyond the Big Bang, beyond even the multiverse. One thing's certain, in the vast thermal tapestry of the cosmos, this icy anomaly burns hotter than ever with unanswered questions. Rising from the heart of our galaxy like twin ghosts stretching halfway to the Andromeda Galaxy, the Fermi Bubbles are one of the Milky Way's most enigmatic structures. Imagine two colossal orbs of scorching hot gas and high-energy radiation, each towering 25,000 light-years above and below the galactic plane, visible only in gamma rays, the universe's highest energy light. These aren't delicate soap bubbles drifting in space. They're titanic remnants of some ancient cataclysm, a violent outburst that must have shaken our galaxy to its core. And the strangest part, we almost missed them entirely. Discovered in 2010 by NASA, a Fermi Gamma-ray space telescope, the bubbles hid in plain sight for decades, camouflaged against the noisy backdrop of cosmic rays and starlight. It took advanced algorithms sifting through years of data to reveal their faint glow, like spotting a whisper in a hurricane. But once seen, they raised an immediate question. What could possibly unleash enough energy to carve such enormous structures into the fabric of our galaxy? The answer might lie with Sagittarius, a star, the supermassive black hole squatting at the Milky Way center. Picture a sleeping dragon that occasionally stirs, unleashing torrents of fire. Around 6 million years ago, Sagittarius, a star, may have done just that, gorging on an immense feast of gas and stars, then belching out twin jets of plasma at near light speed. These jets, slamming into surrounding gas, could have inflated the Fermi bubbles like cosmic bellows, leaving behind a lingering glow of gamma rays. There's even evidence in the bubbles' chemical makeup, traces of elements forged in extreme heat, along with shock waves rippling through their edges like echoes of a long-forgotten explosion. But not everyone's convinced. Some theorists argue the bubbles are too symmetrical, too perfectly balanced to come from a messy black hole feeding frenzy. Their edges are suspiciously sharp, as if traced by an invisible hand. This has led to an even wilder possibility: dark matter annihilation. if dark matter particles, those elusive, invisible bits that outweigh normal matter 5 to 1, collide and annihilate near the galaxy's core, they could release bursts of energy capable of sculpting these eerie structures. It's a tantalizing thought, the Fermi Bubbles as the first visible sign of dark matter's hidden fireworks. Then there's the timing problem. The bubbles seem relatively young, cosmically speaking, yet our galactic center has been quiet for eons. If they are from Sagittarius, a star's last meal, why haven't we seen more recent outbursts? Unless, of course, these explosions are rarer than we thought once in a billion-year events that reshape entire galaxies in their wake. Or perhaps the bubbles weren't made in one violent act, but by a series of smaller eruptions, like a volcano steadily puffing smoke into the sky. Here's what keeps scientists up at night: the Fermi Bubbles might not be unique. Other galaxies could have similar structures hidden in their gamma-ray fog, invisible until we develop the tools to spot them. And if so, they could rewrite our understanding of galactic evolution. Forget serene spirals gently turning in the void. Galaxies might be pressure cookers, periodically venting unimaginable energies into space. The bubbles could even solve another mystery: why some galaxies stop forming stars. The energy pumped out by events like these might blow away the raw materials for new stars, leaving galaxies to fade into quiet middle age. One thing's certain: the Fermi Bubbles are more than just a pretty cosmic anomaly. They're a window into the violent, dynamic heart of our galaxy, a reminder that even the Milky Way, for all its seeming calm, has a temper. And as we stare up at those faint gamma-ray ghosts, we're left wondering, when will the dragon wake again? Here's something that should keep you up at night. The universe is playing a cosmic shell game with its own building blocks. Scientists call it the missing baryon problem, and it's one of those quiet scandals hiding in plain sight. Baryons, ordinary matter like protons and neutrons, make up everything we see: stars, planets, you. But when cosmologists tally up all the baryons predicted by the Big Bang's afterglow, nearly half are unaccounted for. That's like checking your bank statement and discovering half your life savings have vanished without a trace. So where's all this missing matter hiding? The leading suspect: a vast, diffuse ocean of warm, hot intergalactic plasma, or WIM for short. Picture this: enormous tendrils of gas threading between galaxies like cosmic spider silk, so hot they glow in X-rays but too thin to spot with regular telescopes. These filaments form the cosmic web, the scaffolding of the universe, and they could be hoarding the missing baryons in plain sight. The challenge: this gas isn't just faint, it's practically ghostly. Detecting it is like trying to spot a candle flickering behind a foggy window from a mile away. Yet bits of evidence are trickling in. When light from distant quasars passes through these filaments, certain wavelengths get absorbed, fingerprints of the WIM presence. It's like shining a flashlight through mist and seeing where the beam dims. Some studies even suggest the gas might clump into clouds denser than expected, floating in the voids between galaxies like cosmic dew. But even if we confirm the WIM role, another puzzle remains. How did so much matter end up there? The universe seems to have taken its ordinary stuff, the raw material of planets and people, and scattered it into the hardest-to-reach corners imaginable. Then there's the dark horse theory. Some baryons might be hiding in extreme environments, like the atmospheres of rogue planets or the cores of failed stars. Imagine trillions of frozen, nomadic worlds, untethered to any star, drifting through interstellar space with a cargo of locked-away matter. Or neutron stars, those ultra-dense stellar corpses swallowing baryons whole and crushing them beyond recognition. It's a cosmic game of hide and seek, where the hiders might have reshaped themselves into forms we barely recognize. The stakes here are higher than they seem. If we can't find the universe's lost matter, it might mean our models of cosmic evolution are fundamentally flawed. Or worse, that there's physics at work we haven't even dreamed of yet. Every missing baryon is a silent question mark, whispering that even the ordinary parts of reality still have secrets to spill. Long before the first stars flickered to life, the universe was a creeping, suffocating blackness, a thick soup of hydrogen gas so dense it swallowed light whole. Then something extraordinary happened. Over hundreds of millions of years, that impenetrable fog burned away, transforming the cosmos from opaque to crystal clear. Scientists call this the reionization epoch, and it's one of the most pivotal yet least understood chapters in cosmic history. Picture the early universe like a steam-filled bathroom mirror. Initially, you see nothing but haze. Then, as heat rises, patches begin to clear, revealing fragments of your reflection. That's roughly how reionization unfolded, but on a scale so vast it boggles the mind. The trigger, the first generation of stars and galaxies blazing to life in the darkness. These cosmic pioneers didn't just shine, they bombarded space with ultraviolet radiation so intense it stripped electrons from hydrogen atoms, ionizing them in a wave that swept across the universe. One by one, the fog lifted and light could travel freely for the first time. But here's the mystery: reionization didn't happen evenly. Some regions cleared early, others stubbornly clung to their haze, and the differences can't be explained by simple distance or time alone. It's as if someone turned on the lights in a city, but certain neighborhoods stayed dark for centuries. Why? The answer might lie in the uneven distribution of those first stars. Early galaxies weren't sprinkled uniformly like salt. They clustered in dense knots, leaving vast deserts between them. Where galaxies thrived, radiation flooded out, carving transparent bubbles. Where they were scarce, hydrogen lingered like morning mist in a valley. Then there's the role of quasars, the universe's first monsters. These supermassive black holes, gobbling matter at the hearts of young galaxies, belched out torrents of energy that could ionize gas far beyond their home galaxies. Think of them as cosmic blowtorches, clearing fog in concentrated beams rather than broad strokes. Yet even quasars can't explain everything. Some observations suggest reionization began before quasars were common, pointing to an even earlier culprit. Perhaps population, 3 stars hypothetical, hypergiant stars hundreds of times the Sun's mass, blazing briefly but ferociously before vanishing without a trace. These stars would have been ultraviolet factories, shredding nearby hydrogen with ease if they existed at all. But the plot thickens. Recent studies of the cosmic microwave background reveal another wrinkle. Reionization might not have been a single, smooth transition, but a stop-start process with multiple waves. Imagine clearing a foggy window, only for new condensation to form and evaporate again in cycles. This could mean early stars and galaxies flickered on and off as they competed with collapsing gas clouds and supernova explosions, each event resetting the cosmic clock. The implications are staggering. If reionization was patchy and chaotic, it could explain why some of the universe's first galaxies look suspiciously mature, as if they had a head start in clear regions. It might also hint at unseen forces at work, like dark matter's gravitational pull sculpting where stars could form. And here's the kicker: we're seeing this all in hindsight. The light from reionization's final stages is just reaching us now, stretched into radio waves by 13 billion years of cosmic expansion. We're essentially watching the universe's baby pictures develop in real time, one fuzzy snapshot at a time. So what really lifted the cosmic veil? The truth might be messier than we thought. A tug of war between stars, black holes, and invisible structures we're only beginning to map. And with every new observation, we're peeling back another layer of this ancient mystery, uncovering how our universe went from darkness to light, one ionized atom at a time. Hidden deep in the cosmic archives, where ancient light tells stories of a younger universe, there are structures so vast and enigmatic they defy simple explanation: the Lyman alpha blobs. Picture glowing islands of hydrogen gas, each spanning hundreds of thousands of light years, floating in the void like radiant jellyfish caught in a cosmic current. They're named after the specific wavelength of ultraviolet light they emit, Lyman alpha, a telltale sign of hydrogen atoms being energized by something powerful. But what's illuminating these gargantuan clouds? The answer might rewrite how we understand the seeds of galaxy formation. At first glance, these blobs shouldn't exist. Gas this diffuse should have cooled and faded into the background eons ago. Yet here they are, blazing brightly in the distant universe, often clustered around fledgling galaxies or quasars. One leading theory points to the violent birth cries of early galaxies. As stars burst to life in dense pockets of the early cosmos, their intense radiation could have excited the surrounding hydrogen, causing it to glow. Imagine a city's skyline at night, not just the buildings shining, but the very air between them flickering with reflected light. That's the scale we're talking about, but with entire galactic neighborhoods. Then there's the quasar connection. Some of the brightest blobs seem anchored by these ravenous supermassive black holes, whose jets of high-energy particles might be pumping the surrounding gas full of energy like a cosmic defibrillator. But here's the catch: not all blobs have obvious quasars nearby. This has led to wilder ideas like dark matter annihilation. The invisible stuff that makes up most of the universe's mass might be decaying or colliding in ways that release energy, lighting up these gas clouds from within. It's a ghostly possibility, unseen particles painting the cosmos with light. But the real intrigue lies in what these blobs reveal about the universe's adolescence. They're often found in regions teeming with young galaxies, suggesting they might be the scaffolding upon which galaxies assemble. Picture a construction site where gas clouds act like blueprints, marking where matter will eventually clump into stars and galaxies. Some blobs even show filamentary structures, tendrils of gas stretching between galaxies like cosmic bridges, hinting at the hidden highways along which matter flows to build the universe's large-scale structure. Yet mysteries linger. Why do some blobs appear isolated, floating in voids far from any obvious energy source? Could they be relics of even earlier processes, like shock waves from the universe's inflationary period? Or perhaps they're evidence of something more exotic, like primordial black holes seeding pockets of intense radiation. Every new observation adds layers to the puzzle. Recently, astronomers discovered blobs with intricate internal motion swirls and eddies suggesting turbulent histories. It's like finding a whirlpool in what you thought was a placid lake, hinting at currents beneath the surface. What makes Lyman alpha blobs so thrilling isn't just their size or luminosity, it's their refusal to fit neatly into any single box. They might be cosmic nurseries, dark matter laboratories, or something entirely unexpected. And as we peer deeper into their glow, we're not just studying distant gas clouds, we're reading the diary of the universe's youth, written in light that's traveled billions of years to reach us. Each photon carries a question: how much of the cosmic story are we still missing? Imagine two clocks, both built by master craftsmen, both ticking perfectly, yet one runs slightly faster than the other. No matter how many times you check them, the discrepancy remains. That's essentially the crisis cosmologists face with the Hubble tension, a stubborn mismatch between how fast we think the universe is expanding and what we actually observe. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, measurements of nearby stars and supernova peg it closer to 73. 6 kilometers might not sound like much, but in cosmology, it's a chasm, one that could force us to rewrite the rules of the universe. So where's the disconnect? One camp argues it's all about measurement errors. Maybe our tools aren't as precise as we thought, or we're misreading cosmic landmarks like Cepheid variable stars, the universe's mile markers. But here's the catch: as observations pile up, the gap refuses to close. Even cutting-edge instruments like the James Webb Space Telescope, designed to cross-check these measurements, only deepen the mystery. If it's not a mistake, then what? That's where things get spicy. Some theorists point to dark energy, the enigmatic force accelerating cosmic expansion. What if it's not constant, as Einstein's cosmological constant suggests, but evolving? Picture a car that doesn't just speed up, it presses the gas harder over time. Dark energy's strength might have changed across cosmic history, leaving fingerprints in the early universe that don't match today's observations. Or perhaps dark energy interacts with dark matter in ways we've yet to imagine, tweaking the expansion rate like a hidden dial. Then there's the nuclear option, new physics. The Hubble tension might be our first glimpse of forces or particles beyond the standard model, something that alters gravity on cosmic scales. Imagine discovering that the universe has a fifth fundamental force, one that only kicks in across vast distances. It's not as far-fetched as it sounds after all. Dark energy and dark matter already hint at gaps in our understanding. If the tension holds, it could mean cosmology's standard candle methods aren't broken, they're just incomplete. But here's the twist, the tension isn't just a numbers game. It's a philosophical rift. Do we trust the early universe's snapshot, the CMB, more than the local measurements of today? Or is the universe telling us it's more complicated than we assumed? Every proposed solution opens new questions. A tweak to dark energy might unravel our models of galaxy formation. New physics could demand a rethink of the Big Bang itself. And lurking beneath it all is the unnerving possibility that we're not just missing a piece of the puzzle, we might be holding the wrong box entirely. One thing's certain, the Hubble tension isn't just a technical hiccup. It's a tremor in the foundations of cosmology, a signal that the universe still has secrets to spill. And until we solve it, every calculation about the past or future of everything carries an invisible asterisk. A silent admission that somewhere in the numbers there's a story we haven't yet learned to read. Black holes have long been the universe's ultimate vaults, cosmic locksmiths that swallow information and throw away the key, or so we thought. The black hole information paradox is one of physics' most dizzying puzzles, forcing us to confront whether reality itself forgets. It all started with Stephen Hawking's shocking realization in the 1970s. Black holes aren't truly black, they slowly leak energy, emitting what we now call Hawking radiation. And here's the problem. According to quantum mechanics, information, the detailed state of every particle that falls into a black hole, can never be destroyed. But if a black hole evaporates entirely through Hawking radiation, leaving no trace behind, where does that information go? It's like burning a library and claiming the books still exist just in smoke. This contradiction sent physicists scrambling for answers. One radical proposal, firewalls. Imagine falling toward a black hole's event horizon, expecting the quiet darkness of infinite spacetime curvature. Instead, you hit a searing wall of energy, a fiery boundary that incinerates everything crossing it. Firewalls would preserve information by encoding it in the radiation, but at a horrific cost, violating Einstein's equivalence principle, which says free fall should feel like floating in empty space. It's the universe's ultimate catch-22, save quantum mechanics or spare relativity. Then there's the holographic principle, a mind-bending idea suggesting all the information within a black hole isn't lost, it's smeared across its surface like a cosmic fingerprint. Picture a three-dimensional movie projected from a two-dimensional screen. The events inside the black hole might be encoded on its event horizon in tiny Planck-scale pixels, with Hawking radiation carrying that data back into the universe. Recent breakthroughs in string theory and quantum gravity even hint at how this could work, with black holes acting like quantum computers that process and emit scrambled information. But the plot thickens. In 2019, physicists calculated that islands inside black holes could preserve information without firewalls or holograms, regions where space-time curves gently enough to stash data safely. And in 2023, quantum experiments simulating black holes suggested information might escape via entanglement, a ghostly quantum link between particles. It's as if the universe built a backdoor for data to slip through, hidden in the fabric of reality itself. The stakes couldn't be higher. If information can vanish, it undermines the predictability of physics, turning the universe into a capricious storyteller that forgets its own plot. But if it's preserved, we might be staring at the first clues to a grander theory, one that weaves quantum mechanics and gravity into a single tapestry. Every photon of Hawking radiation carries not just heat but a message. Somewhere in their faint glow, the universe's deepest secrets might be hiding in plain sight. On the night of August 15, 1977, a radio telescope in Ohio picked up a signal so striking that the astronomer who discovered it scrawled, "Wow." In the margin of the printout, and the name stuck, for 72 seconds, a narrowband radio burst blazed at precisely the frequency hydrogen emits naturally, 1420 MHz, as if someone had aimed a cosmic spotlight at Earth. Then, just as suddenly, it vanished, never to repeat. Decades later, the wow signal remains the most tantalizing and frustrating hint that we might not be alone. What makes this signal so electrifying isn't just its intensity. It ticked every box on the hypothetical alien hello checklist, a narrow, focused frequency unlikely to occur naturally, drifting slightly as you'd expect from a distant transmitter on a rotating planet. Even its duration, fits 72 seconds, was exactly how long the telescope's fixed antenna could hear any single point in the sky as Earth turned. It's as if the signal knew we were listening, yet despite dozens of follow-up scans, including a comprehensive search by the Very Large Array in 2020, the signal never reappeared. This silence fuels heated debates. Was it a fleeting cosmic coincidence or evidence of intelligence snuffed out before we could reply? One compelling natural explanation points to hydrogen clouds around comets, specifically 2 comets that happened to be passing through that patch of sky in '77. When later tested, though, their emissions didn't quite match WOW's signature. Other theories suggest microlensing, where a distant star's gravity briefly amplified a natural radio source or even a rogue satellite's reflection. But none fit the data as neatly as that original hello. Then there's the chilling possibility we missed our window. If the signal was artificial, its one-time nature suggests a transient source, a beacon blinking on just long enough to be noticed, or worse, a civilization that flickered out before we could answer. Imagine sending a message in a bottle only for the ocean to reclaim it before anyone reads it. That's the haunting legacy of WOW, a whisper across the cosmos that might have been our only chance to know we aren't alone. Recent advances keep the mystery alive. Breakthrough Listen, the most ambitious SETI project in history, now scans WOW's origin point with AI-powered tools far beyond '70s tech. And in 2020, astronomers proposed a new target, a sun-like star in Sagittarius spotted by Gaia satellite data, now suspected to lie exactly where the signal came from. But until we catch that elusive pulse again, or decode its absence, WOW remains a Rorschach test for the universe, proof we're not alone or proof we're desperately alone. The silence holds the answer. Picture the universe's scaffolding, an invisible skeleton of dark matter that dictates where galaxies form and how they move. For decades, simulations have painted a clear picture. Dark matter should clump into dense halos, with smaller subhalos orbiting larger ones like bees around a hive. But when astronomers peer into the real cosmos, something's off. The dark matter we observe isn't as clumpy as the models predict. Instead of dense cores, many galaxies appear embedded in smoother, puffier halos, as if someone took a cosmic blender to the universe's hidden framework. This mismatch isn't just a minor accounting error. It's a gaping hole in our understanding of how structure forms. The most detailed simulations, like the famed Illustris and Eagle projects, suggest galaxies like the Milky Way should be surrounded by thousands of dark matter subhalos, enough to host countless dwarf galaxies. Yet we've found only a few dozen. Where are the rest? One possibility is that dark matter isn't the sluggish, non-interacting ghost we've assumed. Enter self-interacting dark matter, a theory where these invisible particles occasionally bump into each other, smoothing out clumps like hands kneading dough. Observations of colliding galaxy clusters where dark matter seems to lag behind visible matter lend eerie support to this idea, but there's a wilder alternative. Maybe dark matter doesn't exist at all. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently on cosmic scales, eliminating the need for invisible stuff altogether. MUND successfully predicts galaxy rotation curves without dark matter, but it stumbles when faced with the bullet cluster, where gravity's effects clearly separate from visible mass. Yet even here the plot thickens. A new hybrid theory, emergent gravity, suggests spacetime itself might hold the answer, with gravity emerging from the universe's quantum entanglement structure like steam from boiling water. The stakes couldn't be higher. If dark matter is self-interacting, it implies an entire shadow physics hiding in plain sight, a dark sector with forces and particles we've yet to imagine. If gravity is modified, it upends Einstein's legacy. Every observation, from the faintest dwarf galaxy to the largest cosmic web filaments, becomes a clue in this grand detective story. And with experiments like the Vera Rubin Observatory coming online, we're on the brink of mapping dark matter's distribution with unprecedented precision. What we find might not just solve a puzzle, it could rewrite the rules of the cosmos. Deep in the constellation Eridanus, a cosmic cavern stretches more than 1 billion light-years across, a void so vast it could swallow entire galactic superclusters without a trace. This is the Eridanus supervoid, one of the largest structures ever discovered, and its emptiness isn't just eerie. It might hold the key to one of the universe's most stubborn mysteries, the cold spot in the cosmic microwave background. The connection between these two anomalies is so peculiar it forces us to ask, are we staring at a cosmic coincidence or the fingerprints of physics beyond our wildest theories? At first glance, the supervoid's emptiness seems like a fluke, a random bubble in the froth of the cosmos. But when scientists mapped its location against the cold spot, the overlap was uncanny. The cold spot, that enigmatic chill in the afterglow of the Big Bang, sits almost perfectly centered on the void's yawning expanse. Coincidence, maybe. But here's where it gets strange. If a supervoid lies between us and the CMB, light passing through it should lose energy climbing out of its gravitational well, cooling slightly, an effect called the integrated Sachs-Wolf effect. Yet the Eridanus supervoid's size and depth can't fully explain the cold spot's extreme temperature drop. It's like blaming a puddle for a flood. The scales don't match. This mismatch has sparked wild speculation. Some theorists propose the void isn't just empty, it might harbor exotic energy fields left over from the universe's infancy. Imagine a patch of spacetime where dark energy behaves differently, repelling matter more fiercely and stretching the void's boundaries like taffy. Others wonder if the cold spot and void are relics of a cosmic collision, a bruise from a long-ago impact with another universe in the multiverse. It's a radical idea, but not impossible. If true, the Eridanus supervoid could be a window into realities beyond our own, a dent in the fabric of spacetime where the rules we know no longer apply. But there's a catch. Not all scientists buy the link. Some argue the supervoid's sheer size makes it statistically unlikely to align with the cold spot by chance, like rolling dice and getting the same number 100 times in a row. Alternative explanations suggest the cold spot might be a glitch in our measurements, or the shadow of a primordial black hole lurking unseen. The debate rages because the stakes are high. If the void and cold spot are connected, it means the universe isn't just lumpy, it's lopsided in ways that defy our models. the Eridanus supervoid taunts us with questions. Is it a cosmic fossil, a scar from the universe's birth, a laboratory for unknown physics, or just a statistical ghost, a trick of the light in an infinite cosmos? For now, it remains a silent giant, its emptiness echoing with possibilities we're only beginning to hear. When we look at the cosmic microwave background, the faint glow from the universe's infancy, we expect randomness, a smooth scatter of hot and cold spots from the primordial soup. But the universe loves to surprise us. At the largest scales, the CMB shows strange, unexpected alignments in its quadrupole and octupole moments, patterns so peculiar they've sparked debates about whether we're seeing the fingerprints of a finite cosmos or forces we've yet to discover. The quadrupole represents the CMB's second largest fluctuation pattern, like stretching a rubber sheet and seeing where it dips and rises. The octupole is the next tier, a more complex ripple. Both should be randomly oriented with no preferred direction. Instead, they're eerily aligned not just with each other but with the ecliptic plane of our solar system. It's as if the universe's baby pictures were posed deliberately with some invisible hand framing the shot. The odds of this happening by chance, less than 1 in 1,000. So what's behind this cosmic coincidence? One tantalizing idea is that the universe isn't infinite but wrapped in on itself like a hall of mirrors. In a finite cosmos, space could be shaped like a torus or a dodecahedron, with light looping back on itself and creating repeating patterns. Imagine standing in a room where every wall reflects the same chandelier eventually. The reflections align in ways that seem impossible in an open space. The CMB anomalies might be the first glimpse of such a structure, a cosmic kaleidoscope hiding in plain sight. Then there's the magnetic hypothesis. Primordial magnetic fields, woven into the fabric of space-time in the universe's first moments, could have stretched these fluctuations into alignment like iron filings under a magnet. These fields would be relics of a time before atoms, before stars, when the cosmos was a seething plasma of raw energy. If they exist, they'd rewrite our understanding of how structure formed and why the universe looks the way it does. But here's the twist. Skeptics argue these anomalies might just be artifacts of foreground interference, dust in our own galaxy, or even the way we process CMB data could subtly tilt the scales. The Planck satellite's meticulous observations have chipped away at some anomalies, but others stubbornly remain, and that's the heart of the mystery. Are we seeing the limits of our instruments or the limits of reality itself? The stakes are cosmic. If the alignments are real, they could hint at a universe far stranger than we imagined, one with edges or hidden forces threading through the void. If they're illusions, they're reminders of how carefully we must peel back the layers of noise to hear the universe's true voice. Either way, these patterns whisper a question we're only beginning to ask. How much of what we see is the universe, and how much is just the mirror we're holding up to it? In the deep silence between planets, two robotic pioneers drifted toward the stars, carrying not just golden records of human greetings, but a mystery that would baffle scientists for decades. The Pioneer 10 and 11 probes, launched in the early 70s, were the first human-made objects to cross the asteroid belt and send back stunning images of Jupiter and Saturn. But as they sailed beyond the solar system, something strange happened. Both spacecraft began slowing down ever so slightly, as if an invisible hand were tugging them backward. This minuscule deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, a glitch in the cosmic math that refused to vanish. At first, engineers suspected mundane explanations. Maybe escaping gas from the probe's thrusters was creating tiny counterforces. Or perhaps uneven heat radiation from their nuclear power sources was pushing them off course, like sunlight nudging a sunbather's beach ball. But when researchers crunched the numbers, thermal effects could only account for part of the drag. The rest lingered unexplained, a whisper of physics gone awry. That's when the theories got wild. Could the anomaly hint at unseen dimensions where gravity leaks into hidden folds of space-time? Some models of string theory suggest our universe might float within a higher dimensional bulk, with gravity able to seep into these extra realms. If true, the pioneer's slowdown might be the first experimental whiff of these shadowy dimensions. Others proposed modifications to Einstein's general relativity, suggesting gravity behaves differently at extreme distances, gaining strength just enough to tug on distant probes. But the most tantalizing idea, dark matter. What if the solar system is cocooned in a diffuse halo of invisible particles, their collective gravity gently braking the pioneers like a car rolling through molasses? It's a poetic thought, our spacecraft racing into the dark, slowed by the very stuff that holds galaxies together. Then, in 2012, a painstaking analysis of decades-old engineering data delivered a twist. The anomaly wasn't constant. It changed over time, strong evidence that heat radiation was the culprit after all, just in ways more complex than initially modeled. The probe's radioactive power sources had cooled unevenly, their warmth radiating asymmetrically and creating just enough recoil to explain the drift. Case closed, not quite. Some scientists argue the thermal model still leaves gaps, especially for Pioneer 11. And if the anomaly was purely thermal, why did it match predictions of exotic gravity so eerily? The Pioneer's legacy endures. They remind us that even the tiniest inconsistencies can ripple into profound questions about gravity, dimensions, and the invisible architecture of space. Their golden records still spin into the void, carrying messages from a species that races to solve the puzzles its own machines leave in their wake. Every galaxy we've ever observed moves as if it's drowning in an invisible sea of dark matter until now. Meet NGC 1052 DF2, the cosmic rebel that refuses to play by the rules. This ghostly galaxy, floating 65 million light-years away in the constellation Cetus, spins so slowly that according to all our models it should fly apart. Yet it doesn't. Its stars cling together without the gravitational glue of dark matter, defying one of cosmology's most fundamental assumptions. The discovery sent shockwaves through the astronomy community, because if this galaxy is real, it doesn't just challenge our theories, it threatens to upend them. At first glance, DF2 looks like any other ultra-diffuse galaxy, a wispy, translucent sprawl of stars so thinly spread you could see right through it. But when astronomers measured its rotation, the numbers didn't add up. Normally, galaxies rotate so fast that without the extra gravity from dark matter, their stars would be flung into the void like kids on a spinning merry-go-round. DF2, though, moves with the sluggish calm of a galaxy that's barely holding on, its stars tracing lazy arcs that require no invisible mass to explain. It's like watching a car speed down the highway with no engine. Physics says it shouldn't be possible. Cue the skepticism. Some researchers argued the distance to DF2 might be miscalculated, throwing off mass estimates. Others suggested its odd structure, a chaotic jumble of star clusters with no central bulge, could mimic the appearance of a dark matter-free zone, but follow-up observations only deepened the mystery. A second galaxy, DF4, was found with similarly baffling properties, and studies of DF2's globular clusters, usually reliable tracers of dark matter, confirmed the unthinkable. This galaxy really does seem to be missing the universe's most abundant material. So how did DF2 end up this way? One compelling theory points to its neighbor, the massive elliptical galaxy NGC 1052. Billions of years ago, a close encounter might have ripped away DF2's dark matter like a cosmic thief, leaving behind only visible stars. Simulations show such tidal stripping can happen, but never this cleanly. Usually, some dark matter lingers. Another idea is that DF2 formed in a freakish pocket of the early universe where gas collapsed into stars without the usual dark matter scaffolding. Imagine building a house without a frame. It's possible, but it shouldn't stand for long. Then there's the nuclear option. Maybe our understanding of gravity is wrong. The lambda-CDM model, which relies on dark matter to explain cosmic structure, has been astronomy's backbone for decades. DF2's existence could mean dark matter isn't universal, or that alternative theories like modified Newtonian dynamics deserve a second look. But here's the twist. Mund struggles to explain other aspects of DF2, like the bizarre speeds of its globular clusters. It's as if the galaxy is taunting every theory we throw at it. What makes DF2 so electrifying isn't just its defiance, it's the questions it forces us to ask. Is dark matter more complicated than we thought? Could there be types of galaxies that form without it? Or is this a cosmic fluke, a glitch in the grand simulation of the universe? Every new observation tightens the knot. Recent studies suggest DF2 might have some dark matter after all, just far less than expected, adding yet another layer to the puzzle. One thing's certain, NGC 1052 DF2 is more than an anomaly. It's a crack in the foundation of modern cosmology, a reminder that the universe still holds cards it hasn't shown us. And as we stare at this ethereal enigma, we're left wondering, are we seeing the exception that proves the rule, or the first clue that the rule was never right at all? At the very edge of our observable universe, where light barely reaches us after traveling for billions of years, lies a structure so immense it shatters our understanding of cosmic scale, the Hercules Corona Borealis Great Wall. Picture a sprawling filament of galaxies 10 billion light-years long, stretching across the sky like the bones of some celestial leviathan. This isn't just a cluster or a supercluster, it's a cosmic metropolis, a web of galactic neighborhoods so vast it challenges one of astronomy's foundational ideas, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same everywhere, no matter where you're standing. Matter should be evenly distributed like flour sifted through a cosmic sieve. Yet the Hercules Corona Borealis Great Wall defies that expectation. Its sheer size, covering a tenth of the observable universe, makes it a statistical impossibility under standard models. Imagine rolling a pair of dice and getting snake eyes 100 times in a row. That's the level of cosmic improbability we're dealing with here. So how did this gargantuan structure form? The leading theory points to the universe's infancy, when tiny quantum fluctuations were stretched to unimaginable scales by inflation. These ripples in spacetime became the seeds for all cosmic structure, but even then, simulations struggle to produce something this massive. Some scientists suggest the wall might be the imprint of a primordial phase transition, a moment when the infant universe shifted states like water freezing into ice, leaving behind cracks in the fabric of spacetime. Others wonder if dark energy, the force accelerating cosmic expansion, played a role, perhaps by sculpting matter into vast, interconnected sheets before it began dominating the cosmos. Then there's the unsettling possibility that the wall isn't a single structure at all, but a chance alignment of smaller filaments, a cosmic illusion created by our limited perspective. Like standing in a forest and mistaking overlapping branches for one enormous tree. But even if that's the case, the odds of such a perfect alignment are vanishingly small. The wall's existence forces us to confront uncomfortable questions. Is the universe more lopsided than we thought? Or are we missing something fundamental about how matter clumps together? Here's what makes this cosmic titan so thrilling. It's not just a curiosity. If structures like this exist, they could rewrite our models of galaxy formation, dark matter behavior, even the fate of the universe itself. The Hercules Corona Borealis Great Wall doesn't just push boundaries, it draws a line in the cosmic sand and dares us to cross it. Picture a distant galaxy, its light streaming across billions of years to reach your eyes. Now imagine that as the light traveled, it grew fainter not just because of distance, but because the photons themselves were losing energy along the way, like marathon runners growing exhausted before the finish line. This is the essence of tired light theory, a controversial alternative to cosmic expansion, and it's the Tolman surface brightness test that puts this idea under the microscope. When Edwin Hubble discovered the universe was expanding, he did so by observing galaxies' redshifts, the stretching of light as they moved away. But in the 1930s, physicist Richard Tolman proposed a clever way to distinguish expansion from other possibilities. His test hinges on a simple but profound observation. In an expanding universe, a galaxy's surface brightness, the amount of light per unit area, should drop faster with distance than in a static universe where light merely tires. Think of it like two candles. One is moving away while burning steadily, the other stays put but dims over time. The way their glow fades tells you which scenario you're witnessing. For decades, the test seemed to confirm expansion. Distant galaxies appeared fainter by exactly the amount predicted by the Big Bang model, but recently, odd discrepancies have emerged. Some ultra-diffuse galaxies in the early universe look brighter than they should, as if their light hasn't dimmed enough over the eons. Meanwhile, certain quasar populations show the opposite excessive dimming that tired light models struggle to explain. It's as if the universe can't decide which rule to follow. So what's really going on? One possibility is cosmic dust. Intervening clouds of particles could be absorbing or scattering light, mimicking tired light effects. Yet detailed infrared surveys find too little dust to account for the anomalies. Another angle involves galaxy evolution. Perhaps early galaxies were simply more efficient at producing light, their stars packed tighter or burning brighter than we've assumed. But this raises new questions. Why would galaxies fundamentally change their structure just because we're observing them at a younger age? Then there's the radical fringe. A handful of researchers argue the Tolman test's inconsistencies hint at something deeper, a flaw in our understanding of redshift itself. Could photons interact with quantum spacetime foam over vast distances, gradually losing energy? Or might redshift be partly gravitational, caused by climbing out of the deep potential wells of cosmic filaments? These ideas remain speculative, but they underscore how much we still don't know. The real power of the Tolman test lies in its simplicity. It doesn't require complex instruments or untested physics, just careful observations of how light behaves across the ages. And that's what makes the current puzzles so tantalizing. Whether they point to overlooked astrophysics or something more revolutionary, they remind us that even the oldest tools can uncover fresh mysteries when we dare to look deeper. Galaxies shouldn't have favorite numbers, yet when astronomers measure their redshifts, the results keep clustering around specific values like a cosmic dial stuck on preset stations. This bizarre phenomenon, known as redshift periodicity, suggests galaxies might be arranged in concentric shells around Earth, a finding so controversial it sparked decades of debate. Are we seeing the architecture of a quantized universe or just the echoes of our own observational blind spots? The story begins in the 1970s when astronomer William Tift noticed something odd. While studying spiral galaxies, their redshifts normally expected to vary smoothly appeared to jump between discrete intervals as if space itself had a hidden grid. Later studies reinforced the pattern, with galaxies seeming to prefer redshifts separated by roughly 72 kilometers per second. It's as if the universe were a giant piano, and every galaxy was hitting the same notes in a cosmic scale. Skeptics were quick to pounce. Couldn't this just be an artifact of how we measure Doppler shifts or the quirks of telescope sensitivity? Yet the signal persisted across independent datasets even as instruments improved. That's when the theories got wild. One camp proposed that redshift quantization hints at a pixelated universe where spacetime itself is granular, with galaxies snapping into preferred positions like marbles settling into the dimples of a pegboard. Imagine the cosmos as a vast digital display, with reality rendered at a resolution so fine we've only just glimpsed its edges. Then there's the holographic angle. If the universe encodes information on two-dimensional surfaces, as some quantum gravity models suggest, redshift periodicity might reflect underlying vibrational modes like the harmonics of a plucked string. Even more radical is the idea that these shells are evidence of a cyclic universe, with each layer representing a separate bounce from a previous contraction phase. Picture an onion where each skin marks a rebirth of spacetime, but let's not dismiss the mundane. Some astronomers argue these patterns emerge from the way galaxies form along the cosmic web's filaments, creating natural spacing that looks periodic from our vantage point. Others point to subtle biases in how we select galaxy samples, like counting trees in a forest but missing the ones hidden behind thicker trunks. What makes this debate so electrifying is the stakes. If redshift quantization is real, it challenges not just our maps of the cosmos, but the very nature of reality. Are we living in a universe with built-in harmonics, a place where even emptiness has rhythm? Or are we chasing shadows, mistaking the tremors of our instruments for the music of the spheres? Until we know for sure, those stubborn peaks in the data will keep whispering a tantalizing question: what if the universe is playing a tune we're only beginning to hear? We might feel like cosmic royalty living in the Milky Way, but here's the humbling truth. Our galactic neighborhood is floating inside one of the universe's emptiest rooms, the KBC Void. Named after the astronomers who discovered it, Keenan, Barger, and Cowie, this colossal bubble stretches over 2 billion light-years across, making it the largest known void in existence. And we're right in the middle of it. Picture a balloon with a handful of glitter inside, most of it clumped on the edges, leaving the center eerily sparse. That's us, a few scattered galaxies adrift in a sea of near-nothingness. But the real mystery isn't just the void's size, it's what this emptiness means for our understanding of the universe's expansion. You've probably heard of the Hubble constant, the number scientists use to measure how fast the cosmos is stretching. Here's the problem: depending on where we look, the numbers don't match. Measurements from nearby galaxies suggest a faster expansion rate than those taken from the afterglow of the Big Bang, and the KBC Void might be the reason why. Think of it like running through a crowd. If you're in a dense mob, you'll bump into people constantly, slowing you down. But if you're sprinting across an empty field, you'll move faster with nothing holding you back. Our galaxy's location in this underdressed void means we're essentially in that empty field, less gravitational drag from surrounding matter, making nearby space seem to expand quicker than it really is. It's a cosmic optical illusion, one that could explain why our local measurements clash with those from the early universe. Now, here's where it gets even stranger. If the KBC Void is real and not just a statistical fluke, it challenges one of cosmology's bedrock principles, the idea that the universe is roughly the same everywhere when you zoom out far enough. Called the cosmological principle, this assumption guides everything from galaxy formation models to dark energy theories, but a void this massive throws a wrench into that tidy picture. How could such a lopsided bubble form? Did some titanic force carve it out, or is the universe far more uneven than we ever dared imagine? Some scientists argue the void could be a fossil from the universe's infancy, a relic of quantum fluctuations stretched to unimaginable scales by inflation. Others wonder if dark energy, the mysterious force accelerating cosmic expansion, behaves differently in these barren regions, sculpting voids like bubbles in boiling water. And then there's the spine-tingling possibility that we're not in a special place at all, that the cosmos is riddled with voids this size, and we just haven't found them yet. But perhaps the most unsettling implication is this: if our measurements of the universe's expansion are skewed by the void, what else are we getting wrong? The Hubble constant isn't just some abstract number. It's the yardstick we use to measure the age, size, and fate of everything. A discrepancy here could mean recalculating the universe's timeline, or even rethinking how dark energy works. It's like discovering your tape measure has been stretched all along, throwing every blueprint into doubt. So next time you look up at the night sky, remember, those glittering stars aren't just above you, they're the few neighbors peeking through the cosmic fence of an unimaginably vast emptiness. And the more we learn about this void, the more we realize how much it's quietly shaping our view of everything beyond it. Take our Milky Way, a grand spiral galaxy with hundreds of billions of stars, all swirling in a delicate dance held together by gravity. Now imagine the cosmic scaffolding it should sit upon, a vast swarm of thousands of tiny satellite galaxies, each a faint whisper of stars clinging to our galaxy's gravitational pull. At least that's what our best simulations predict, but when astronomers peer into the night sky, they find only a few dozen of these dwarf galaxies. This glaring mismatch between theory and reality is known as the missing satellites problem, and it's been gnawing at cosmologists for decades. The problem runs deep. Supercomputer models of dark matter, the invisible glue that shapes cosmic structure, suggest cold dark matter particles should clump into countless small halos around galaxies like ours. These halos act as gravitational traps, pulling in gas to form stars and birth dwarf galaxies, yet the universe seems to have skipped most of these steps. Where are all the expected satellites hiding? One possibility is that they are there, we just can't see them. Some halos might be too dim, their stars scattered too thin, like ghost towns lost in the galactic outskirts. Others could be dominated by dark matter alone, barren of stars entirely. Recent ultra-sensitive surveys have uncovered a few more ultra-faint dwarfs, but the numbers still fall woefully short. That's where warm dark matter enters the scene. Unlike its cold cousin, this hypothetical particle would be lighter and faster moving, smoothing out those tiny density fluctuations in the early universe. The result, fewer small halos form, bringing simulations closer to the sparse dwarf counts we observe. There's just one catch. Warm dark matter also struggles to explain other cosmic structures, like the intricate filaments of the cosmic web. It's as if we've found a key that fits the lock but won't turn. Then there's baryonic feedback, a fancy term for how ordinary matter fights back. Gas falling into small halos isn't passive. It heats up, gets blasted by supernova, or pushed around by newborn stars. These processes can strip away star-forming material or even disrupt the halos entirely. Picture trying to fill a leaky bucket during a hurricane. Some simulations now show that when these violent baryonic effects are included, fewer dwarfs survive to the present day. The universe, it seems, might be playing a brutal game of survival where only the fittest mini-galaxies make it, yet mysteries linger. Why do some dwarfs, like the Large Magellanic Cloud, thrive while others vanish? Could reionization, the universe's early ultraviolet fog lifting, have sterilized many halos before stars could form? Or are we seeing the aftermath of galactic cannibalism, where bigger dwarfs consumed their smaller siblings like cosmic krill? The answer might be all of the above. What makes this puzzle so thrilling isn't just the missing dwarf, it's what they reveal about dark matter's nature and the violent adolescence of galaxies. Every faint smudge of starlight in the night sky is a survivor, a clue to forces that shaped the cosmos long before our sun flickered to life. And as telescopes grow sharper, probing deeper into the shadows, we might yet find the universe has been hiding its smallest secrets in plain sight all along. The universe loves its cosmic drumrolls, those split-second blasts of radio waves so powerful they outshine entire galaxies for mere milliseconds. Fast radio bursts, or FRB, have been baffling astronomers since their discovery in 2007. But the real twist came when we caught a handful of these bursts doing something extraordinary, repeating, not just once but over and over, like a distant lighthouse flashing on a schedule only it understands. Suddenly, the question wasn't just what are these things, but what kind of cosmic powerhouse can keep this up without burning out? At first, the leading suspects were neutron stars, those ultra-dense stellar corpses spinning at dizzying speeds. When two neutron stars collide, the resulting fireworks could theoretically produce a one-off FRB. But repeaters, that's a different beast entirely. Imagine a celestial drummer pounding the same rhythm for years, even decades. Some repeating FRBs, like the famous FRB 1211-2, have been firing off bursts since we first detected them, their patterns erratic yet persistent. This points to a source that isn't just surviving a cataclysmic explosion, but thriving long after. Magnetars neutron stars with magnetic fields so strong they could strip the electrons off atoms from a million miles away are prime candidates. Their crust-quaking starquakes might unleash repeated bursts like a fractured bell ringing each time it's jostled, but not everyone's convinced. The sheer energy of some FRBs strains even magnetar physics. Take FRB 200520, a repeater that, in 2020, unleashed a burst so intense it momentarily scrambled Earth's ionosphere. That's not just a starquake, it's a cosmic tantrum, which is why a handful of researchers have dared to whisper the unthinkable: could these be artificial? The idea isn't as far-fetched as it sounds. A civilization advanced enough to harness stellar energies might use focused radio beams for propulsion, communication, or even as galactic lighthouses. The repeating patterns could be signatures of machinery, like a runaway power generator cycling on and off, or a beacon aimed deliberately across the cosmos. Here's where the science gets deliciously messy. Natural explanations keep gaining ground. In 2020, astronomers traced one repeater back to a magnetar in our own galaxy, seemingly closing the case. Yet the diversity among FRBs, some repeating predictably, others sporadically, some with bizarre downward frequency drifts, suggests we might be dealing with multiple phenomena wearing the same disguise. It's like hearing footsteps in the dark and realizing some are raindrops, some are crickets, and maybe, just maybe, one set belongs to something you've never seen before. The stakes sky high. If FRBs are natural, they're probes into the universe's most extreme environments, where matter is shredded by forces we can't replicate on Earth. If even one has an artificial origin, it rewrites humanity's place in the cosmos. For now, every new repeater discovered adds another piece to the puzzle, and another question to the growing list. Are we listening to the death throes of stars, the hum of alien engines, or something even stranger? The universe, as always, is in no rush to tell us. Is the universe a boundless expanse stretching endlessly in all directions, or is it secretly finite? A cosmic hall of mirrors where traveling far enough could bring you back to where you started. This isn't just philosophical musing, it's a question at the heart of cosmology called the universe's topology, and the answer might rewrite everything we thought we knew about reality. Picture space as the surface of a donut. Yes, a donut. Mathematicians call this shape a torus, and if the universe were structured this way, moving in a straight line would eventually loop you back to your starting point. Stars, galaxies, even light itself would wrap around, creating eerie repetitions in the sky. You wouldn't see infinite space, you'd see the same patch of cosmos from different angles, like standing between two mirrors and watching your reflections cascade into infinity. The mind-bending part: a finite universe like this wouldn't need edges or boundaries. It could be both unimaginably vast and curiously self-contained. But how would we even detect such a shape? Astronomers hunt for clues in the cosmic microwave background, the afterglow of the Big Bang. If space were a torus, opposing circles in the CMB's temperature fluctuations should match like puzzle pieces, ghostly echoes of light that loop the cosmos multiple times. Some researchers claim to have spotted these matched circles in the data, though the evidence remains controversial. Other models propose even wilder topologies, like a dodecahedral universe where space folds into 12-sided symmetry, or a Klein bottle, a shape so twisted it merges inside and outside into a single surface. Then there's the infinite scenario where space truly has no end. here's the catch: even infinity might not mean what you think. An endless universe could still be studded with repeating patterns, like a fractal where the same structures recur at every scale. Or it might be uniformly featureless, a vast desert of homogeneity where every observer, no matter where they stand, sees roughly the same cosmos. The stakes. They're cosmic. A finite universe would imply a fundamental scale to reality, a grand architecture hidden in plain sight. An infinite one opens doors to multiverses and regions so distant their light will never reach us. And lurking beneath it all is a humbling thought. Our entire observable universe, with its billions of galaxies, might be just a speck in something far stranger, a shape we're only beginning to trace in the faint glow of ancient light. At the smallest scales, imaginable trillions of times tinier than an atom, space-time itself might not be smooth and continuous, but churning with violent fluctuations known as quantum foam. Picture an ocean's surface during a storm, with waves and bubbles constantly forming and vanishing. Now shrink that frenzy down to the Planck scale, where spacetime itself boils with microscopic turbulence. This isn't just theoretical whimsy, it's a prediction of quantum gravity, suggesting that the very fabric of reality is a seething, frothy chaos at its foundation. But here's the cosmic twist. What if this infinitesimal turmoil isn't confined to the ultra-small? What if, over billions of light-years, quantum foam leaves fingerprints on the light traveling through it, subtly distorting our view of the universe? Consider starlight that's journeyed for eons to reach us. Each photon has traversed an almost unfathomable distance, and if spacetime is granular at heart, those tiny bumps and ripples could accumulate like pebbles in a shoe. The effect might be minuscule for any single photon, perhaps a slight change in direction or energy, but multiply that across the lifetime of the cosmos, and suddenly, the pristine images of distant galaxies in our telescopes might carry hidden distortions, like reflections in a funhouse mirror we don't realize is warped. Some theorists argue this could explain anomalies in the light from quasars, where certain wavelengths seem subtly scattered in ways standard physics can't account for. The stakes get even higher when we think about the cosmic microwave background. This ancient light, a relic from the Big Bang, has traveled nearly 14 billion years to reach us. If quantum foam roughened its path, it might leave statistical oddities in the CMB's temperature fluctuations patterns that look just a little too smooth or clumpy in certain spots. Intriguingly, some of the CMB's anomalies, like the infamous axis of evil, could hypothetically trace back to such granularity. It's like listening to a symphony and realizing the violins are ever so slightly out of tune. Not enough to ruin the music, but enough to hint that the instruments themselves might be flawed. Then there's the wild card, Lorentz invariance violation. Most theories assume the laws of physics work the same no matter where you are or how fast you're moving. But if quantum foam exists, it might break this symmetry at extreme scales, meaning light's behavior could change depending on its energy or travel distance. Imagine two runners on a path, one sprinting, the other walking, but the ground beneath them subtly alters their strides. High-energy gamma rays from distant blazars already show puzzling delays compared to their lower-energy counterparts, as if spacetime itself were dragging its feet. Could quantum foam be the culprit? Of course, skeptics abound. Detecting spacetime's graininess directly would require probing scales a billion times smaller than the Large Hadron Collider can manage. And without a full theory of quantum gravity, we're left with educated guesses. Some models, like loop quantum gravity, predict foam-like structures, while others, like string theory, suggest comma geometries. But here's the tantalizing possibility. If quantum foam does leave marks on ancient light, we might already have the data to find them hidden in the cosmic archives, waiting for the right theory to decode their whispers. So the next time you gaze at a Hubble Deep Field image, remember, those glittering galaxies might be more than just distant suns. They could be cosmic messages, subtly altered by the very fabric of reality's roughest edges, hinting that the universe, for all its grandeur, might be pixelated at its core. Dark energy isn't just some passive backdrop to cosmic expansion. It's the universe's most enigmatic puppeteer, tugging space-time apart with invisible strings. But here's the twist. We've long assumed it behaves like a cosmological constant, its strength unwavering across time and space. What if that's wrong? What if dark energy evolves, growing stronger or weaker as the cosmos ages? The answer could rewrite the universe's fate, from a slow fade to oblivion or a violent big rip that shreds reality itself. The key lies in dark energy's equation of state, a deceptively simple ratio labeled W. For a cosmological constant, W equals -1, meaning dark energy's repulsive force stays locked like a dial turned to maximum. But if W strays from that value, if it becomes more negative or even varies over time, everything changes. Imagine stepping on a car's gas pedal only to discover it sinks deeper the longer you press. That's a universe where dark energy intensifies, accelerating expansion until galaxies, stars, and eventually atoms are torn apart in a catastrophic big rip. On the flip side, if W drifts towards zero, dark energy might weaken, allowing gravity to regain control. The result, a cosmic rebound, collapsing everything back into a fiery crunch, a cycle of death and rebirth stretching across eternity. So how do we measure this phantom parameter? One clue comes from supernova. By tracking how the universe's expansion rate has changed over billions of years, these exploding stars act as cosmic dipsticks. Recent studies of Type Ia supernova hint that W might not be constant after all. It could oscillate slightly, as if dark energy itself is breathing. Then there's the cosmic microwave background, where subtle wrinkles in the Big Bang's afterglow encode how dark energy battled gravity in the universe's youth. Combine these with galaxy clustering data, and some models suggest W was less negative in the past, meaning dark energy is growing stronger. It's like realizing the universe's brakes are failing faster than we thought. But the plot thickens. Some theories propose dark energy isn't even a true energy at all, but a symptom of modified gravity, a breakdown in Einstein's equations on cosmic scales. Others imagine it as a dynamic field called quintessence, rolling down some unseen cosmic hill, its potential energy shifting as it goes. The wildest ideas invoke extra dimensions, where dark energy leaks into our universe from hidden realms like water seeping through cracks. Each scenario predicts a different dance for W, leaving fingerprints we're just learning to read. Here's what makes this search so urgent. If dark energy is evolving, we might be living at a privileged moment, a sliver of cosmic time where its effects are noticeable enough to study, but not so overwhelming that they've erased all other clues. Future telescopes like the Roman Space Telescope aim to nail down W with razor precision, potentially catching it in the act of change. Until then, every measurement carries the weight of cosmic prophecy. Will the universe end in ice, fire, or something stranger? The answer might be hiding in the dark, deep in the heart of our galaxy, where stars crowd so thickly they blur into a golden haze. An invisible fire rages, a torrent of gamma rays with no obvious source. This is the galactic center excess, a mysterious glow that bathes the Milky Way's core in high-energy light, and it's been teasing astronomers with one stubborn question. Are we seeing the last gasp of ancient stellar corpses, or the first whispers of dark matter's demise? At first glance, the culprit seems obvious. Pulsars, the dense, rapidly spinning remnants of dead stars, are prolific gamma-ray factories. As these cosmic lighthouses whirl, their intense magnetic fields accelerate particles to near-light speeds, creating beams of radiation that sweep across the sky with metronomic precision. Thousands of these dim, millisecond pulsars could plausibly lurk in the galactic center, their combined glow masquerading as a smooth excess. There's just one problem. When astronomers scour the region with radio telescopes, they find far fewer pulsars than the gamma-ray signal suggests. It's like hearing a symphony but only spotting a handful of violinists whereas the rest of the orchestra. That's where dark matter enters the stage. If these gamma rays aren't from pulsars, they might be the death throes of invisible particles colliding and annihilating in the galaxy's gravitational well. Picture two specks of dust in a sunbeam vanishing in a flash as they touch, except here, the dust is made of hypothetical weakly interacting massive particles, or WIMP, and the flash is a gamma-ray photon. The galactic center, packed with dark matter, would be the ideal hunting ground for such events. Some models even predict the excess's energy spectrum and spatial distribution match what WIMP annihilation should produce. It's a tantalizing alignment, like finding a key that fits a lock we've never seen. But the plot twists again. Recent analyses suggest the excess isn't perfectly smooth. It might have subtle clumps, as if peppered with faint point sources too dim to resolve individually. That's bad news for dark matter, which should distribute particles evenly, but great news for pulsar proponents. Yet even these clumps defy easy explanation. Are they undiscovered pulsars or something stranger? Some theorists propose intermediate mass black holes, dragging stars into frenzied orbits that emit gamma rays. Others wonder if cosmic rays' high-energy protons slamming into gas clouds could contribute to the glow. The stakes are cosmic. If this is dark matter, it's our first direct glimpse into a hidden universe that outweighs the visible 5-to-1. If it's pulsars, it means the galactic center is even more crowded with stellar zombies than we imagined. And if it's neither, well, that's when physics gets really interesting. Every photon from that mysterious glow carries a message. We just haven't learned to read it yet. The universe is barreling toward an inevitable finale, but what that finale looks like depends on which cosmic force wins the ultimate tug of war. Right now, dark energy is in the driver's seat, accelerating expansion so fiercely that galaxies beyond our local group will eventually vanish from view, their light stretched into oblivion by the relentless stretching of space. This is the heat-death scenario, the slowest and quietest apocalypse imaginable. Picture an ocean where every wave has smoothed to glass, every drop of energy so evenly dispersed that nothing can stir. No stars ignite, no planets orbit, just a vast, featureless void where even black holes have evaporated into faint puffs of radiation. Entropy wins. The universe becomes a graveyard of equilibrium, frozen at absolute zero, with no memory left of galaxies or life. But heat-death isn't the only option. If dark energy weakens or reverses, gravity could reclaim its throne. Imagine the expansion slowing, halting, then reversing as every galaxy, every atom, is dragged back toward a single catastrophic point, the Big Crunch. It's the cosmic opposite of the Big Bang, a collapse so violent it would shred spacetime itself. Black holes would merge into a monstrous singularity, temperatures soaring to infinity as the universe implodes. Some theories suggest this isn't an end, but a reboot, a big bounce where the crunch triggers a new Big Bang, birthing another universe in an infinite cycle of expansion and contraction. Our cosmos could be just one link in an endless chain, each iteration subtly different, like pages in a book no one's written yet. Then there's the wild card, vacuum decay. What if the universe isn't in its true ground state, but teetering on a precarious ledge? Quantum fields underpinning reality could be metastable, like a frozen lake moments before cracking. If a single bubble of true vacuum formed anywhere, anytime, it would expand at light speed, rewriting the laws of physics as it goes. One instant you're sipping coffee, the next atoms can't bind, light can't travel, and existence as we know it ceases. The kicker, it might have already happened somewhere beyond our cosmic horizon, and we'd never see it coming. The irony, we're left guessing our fate based on forces we barely understand. Dark energy's strength, gravity's reach, even the stability of the vacuum, all unknowns. the universe might be a one-act tragedy, an endless drama, or a ticking bomb. And with every measurement of distant supernova or whispers from the CMB, we're not just mapping the cosmos, we're reading its last will and testament. Imagine discovering that everything you've ever known, the stars, the laws of physics, even your own thoughts, might be nothing more than lines of code in an unfathomably advanced simulation. This is the simulation hypothesis, a mind-bending idea that our universe isn't the base layer of reality, but an artificial construct like an ultra-immersive video game running on some cosmic computer. And what makes this more than just sci-fi speculation are the eerie breadcrumbs scattered throughout modern physics. The universe's uncanny mathematical precision, the pixel-like graininess of space-time at the smallest scales, and quantum behaviors so strange they seem less like natural laws and more like glitches. Start with the numbers, the fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, are fine-tuned to absurdly precise values. Tweak any of them even slightly, and stars wouldn't ignite, atoms wouldn't form, and life as we know it would be impossible. It's like walking into a room with 1,000 dials, all set to exactly the right positions to sustain existence. The odds of this happening by chance are so astronomically low that some scientists argue it's more plausible we're in a designed reality, where these parameters were deliberately input. After all, if you were a civilization running universe-scale simulations, you'd optimize the rules to keep them stable and interesting, wouldn't you? Then there's the pixelation problem. At the Planck scale, 10 to the power of -35 meters, spacetime itself might dissolve into a froth of quantum fluctuations. This isn't just theoretical. Experiments with high-energy particles suggest there's a fundamental limit to how small measurements can get, like a cosmic resolution limit. In a simulation, this makes perfect sense. Even the most advanced software has to render reality in discrete chunks. The universe's pixels might just be vanishingly small. And what about quantum mechanics, particles that exist in multiple states until observed, entangled pairs communicating instantly across light years, wave functions collapsing when measured? These aren't just weird, they're suspiciously weird, like optimized code that only loads details when a player looks at them. Even the notorious double-slit experiment, where particles behave differently when watched, feels like a performance for an audience. As physicist James Gates discovered, the equations governing quarks and electrons contain error-correcting codes, the same kind used in computer programs to prevent data corruption. Coincidence or cosmic clue? But here's where the debate ignites. Critics argue that just because reality feels coded doesn't mean it is. The fine-tuning problem might have simpler explanations, like an undiscovered multiverse where every possible constant setting exists across infinite universes. We just happen to live in the one where the numbers work. As for quantum oddities, they might reflect deeper layers of physics we haven't cracked yet, not digital shortcuts and that pixelated space-time. It could be a sign of quantum gravity's granular nature, not proof we're in a rendering engine. Yet the most unsettling question isn't whether we could be in a simulation, it's how we'd ever know. A flawless simulation wouldn't leave obvious bugs, and any programmers would likely hide their tracks. Unless they want us to find them. Some theorists suggest we might uncover signatures in high-energy particle collisions, or by probing the limits of quantum computation. Others propose hunting for cheats, cosmic inconsistencies where the simulation cuts corners, like repeating textures in a video game. But perhaps the real revelation isn't the answer, but the question itself. The simulation hypothesis forces us to confront how little we understand about reality's true nature. Whether we're in a matrix or not, the universe's mysteries, its mathematical elegance, its quantum quirks, its unresolved edges, invite us to keep digging, testing, and wondering. After all, if this is a simulation, the greatest trick might be convincing us it's the only reality there is. And if it's not, well, the truth is probably stranger than we've even imagined. From the Great Attractor's invisible pull to the eerie silence of the wow signal, from the pixelated quantum foam beneath reality to the simulation hypothesis that questions existence itself, we've journeyed through 30 of the universe's most baffling mysteries, each one peeling back another layer of the cosmos's infinite enigma. These aren't just curiosities, they're cosmic crossroads where our understanding of physics, time, and even reality itself bends and shatters. Think about it. Dark flow tugging galaxies toward the unseen, the cold spot hinting at collisions with other universes, rogue galaxies like DF2 defying the very glue that holds the cosmos together. Every mystery we've explored isn't just a gap in our knowledge, it's a doorway to a deeper truth, waiting to rewrite the textbooks. What makes these enigmas so thrilling isn't just their strangeness, but what they reveal about our place in the grand scheme. We're not just observers of the universe, we're detectives piecing together a puzzle where the pieces keep changing shape. The Hubble Tension, the missing baryons, the Fermi Bubbles, each one forces us to ask, are we missing something fundamental, or is the universe far wilder than we ever dared imagine? And let's not forget the quiet revolutionaries like the KBC Void or the Axis of Evil, quietly dismantling the assumption that the cosmos is uniform and predictable. But here's the real magic. These mysteries belong to all of us. They're not locked away in labs or buried in academic papers. They're written across the night sky, waiting for anyone with curiosity to look up and wonder. So tell me, which of these cosmic riddles keeps you up at night? Is it the phantom pull of dark flow, the haunting emptiness of the Boötes Void, or the spine-tingling possibility that we're living in a simulation? Drop your favorites in the comments. I read every single one. And if you're hungry for more mind-bending journeys to the edge of reality, hit subscribe. The universe has countless secrets left to spill, and together we'll be here to uncover them. Until next time, keep looking up and questioning.